Alright, ladies and gentlemen, welcome to Erosion and Deposition Part 2. This is a continuation of the Erosion and Deposition video that we had been recording previously. I will put a link up in the corner of this video, and you will be able to link to the first one if you missed it or if you want to watch it again. So, like we always say, if you like this video, if you find it useful, feel free to like and subscribe, share it wherever you'd like, send it to your friends, get as many people to join up as possible so we can keep making cool videos for you. Otherwise, just enjoy it. Once again, if you need to slow down, stop, pause, rewind, or anything like that while you're watching the video, feel free to do it. But otherwise, let's get going. Alright, so the first type of erosion that we're going to talk about today is going to be wind erosion and the subsequent deposition. So when we're talking about wind erosion, we're talking about those weathered particles, those sediments, that are going to get moved by the movement of air from one point in space to another due to pressure differences. We will talk about the causes of wind and how it blows and why it blows the way it does later on when we get to weather. Keep an eye out for those videos. But right now we're just talking about the movement of sediments through those particles, through those forces I should say, and the depositions that are formed as that process goes forward. Now when we talk about wind erosion, we have to talk about, well, how does it actually move those different sediments? Okay, well, basically what's going to happen is as the wind blows from one point to another point, the particles that are there are going to get, some are going to get suspended in the air if they're really light, some of them are going to get bounced along the ground. There's three main ways in which this happens. You can get the creep, where larger particles like these right here kind of get pushed along, but they never leave the surface, so they kind of like roll along the ground. You get saltation, where the particles are actually going to jump as they move. Okay, as they move from one point into another point. Sometimes they're going to hit each other or hit the ground. We call this attrition. And what's going to happen is those sediments are going to get further weathered and they're going to break down into smaller and smaller pieces. Saltation literally comes from the Latin meaning to jump. In Spanish, at least, saltar is to jump. And then we have those particles that are going to have relatively low densities that can be carried for great distances just floating in the air without having to be along the ground. So very, very fine, very, very small particles are going to be capable of being eroded, being carried from one point in space to another due to what we call suspension. So you have creeping, saltation, and suspension. And you can actually see this in action in the image that you see on your screen right now, which is a massive amount of sand being blasted off the coast of Africa going into the Atlantic Ocean. Okay, and you can see how far it's extending out here. Depending on the strength of the wind and the size of the particles, sometimes these particles again will reach all the way across the Atlantic, and there have been several times where there have been massive dust storms in places like the east coast of Brazil and things like that, as these massive amounts of sand just manage to get pushed across by these atmospheric winds from one continent to the other. So it's an interesting way to imagine sediments from one continent ending up on another. Not to mention all the stuff that's going to end up at the bottom of the ocean. This was kind of a cool looking image. I just thought it was just quite impressive what our planet is capable of doing. Now, once you have all that erosion going on, you're obviously going to be able to get some sort of deposition, wind deposition occurring. Now, this can happen in a lot of different ways, since quite often the particles that you're going to be talking about are sand size. A lot of these are going to be using the sand term to kind of describe what's going on. So the first thing that we have are what we call sand sheets. So sand sheets are these huge flat plots of land with sand particles that are too long to be kind of jumping around. So they just kind of get pushed along the ground there, and you end up with these wide open expanses that are very, very flat. They don't have a whole lot of undulation in them, maybe a little bit, but they're huge, just flat plots of land completely and totally covered in sand, like you see in the image before you now. So here you have this huge flat open expanse, just chock full of just sand particles that are just there. Okay, quite a striking image if you do ask me. Now the next type of deposition is called a sand dune. You've all seen these either in images or maybe you've seen them in person. You get them in deserts and places like that, where you basically just get wind that deposits sand on top of other sand on top of other sand until you get this small little mound of sand that is beginning to form, and it can get quite impressive and quite large. And so here in the image you can see some sand dunes. And the interesting thing about sand dunes is that we can actually track their movement and understand them, and we've actually caught them in real time drifting from one point to the other. So you can actually see how this sand dune is creeping forward as the wind-blown sand is moving particles from one part of it to the other. In paleontology, we sometimes discover creatures that have been buried in sand dunes and what we call aeolian deposits, and this allows us to understand a lot of what's going on there. So we have seen sand dunes that are millions of years old recorded in the fossil record, sometimes with creatures inside of it. It's quite an impressive sight. These things can be quite beautiful and majestic, and I don't know, just something about these images is quite relaxing. I don't know if that's just me, but they are quite impressive. The next type of depositional feature are what we call sand ripples, okay, and these can be quite beautiful, and they form as you get sand that's just laying there and the wind blows across it, and so it creates these little paths along them that kind of look like, to me, either sand, the ripples that you might see created in the ocean, or in this image it kind of looks like the patterns that you might see in a brain that you've seen. This is quite an impressive image. In fact, I think this is one of the images that was used as a background standard in one of the operating systems that has been around for a few years. But you know, using good processing power on a computer, you can see why you'd want to put an image like this. So here we just have our sand ripples, just very pretty, and you can almost hear the sand that would have gouged those tiny little paths along the sand that you can see in the image in front of you. Now, moving on from sand, we're going to move to running water and the erosion and deposition caused by that. So when we're talking about this, we're going to be talking about running water. Just means usually fresh water that is draining or moving at least across the continents, any of the continents that we have here, and flowing into larger bodies of water and quite usually into the ocean at large. So we're talking about rivers and streams and creeks and all these things. Now, while the strength and the speed of those things may be different, the processes that are happening in the Mississippi and in a tiny little creek in your backyard are all basically the same. So we can kind of view them as just one thing that we are talking about. Now, when we talk about running water, we have to understand, well, where does this water come from? Well, all rivers and streams, whether it be the Amazon or the East River, are all going to begin as what we call sheet flow, and that is all going to come from what we call meltwater or runoff. So meltwater is when you get a glacier or an ice cap or just a very large pile of snow that begins to melt and the water starts to flow out of it in the liquid form instead of the solid form that was in before. Or runoff is when you get the water that precipitates out of the sky that collects on the ground and flows and runs off from the point where it hit to something else. The process by which both of these happen is what we call sheet flow. Sheet flow is just this process where all the water that lands in a particular area flows down an incline, collects, and develops into tiny little channels. Those tiny little channels turn into creeks. Those tiny little creeks turn into brooks, or the other way around. I never knew which one was bigger than the other. And then you get small streams, and then smaller rivers, and then larger rivers, and then major rivers, and all the things that we have studied before. And so basically what you're going to start off with is, here's your meltwater. You have a glacier here. As the water comes out of this, as this melts, you're going to get these channels of meltwater that form here. Eventually those are going to collect, flow down if you're on an incline, and eventually flow into a river, as they do in many places around the world. Or you could just get simply a case where you get rain coming out of the sky. That rain hits the mountainside, flows down the incline, and you get the creation of a river. And so that process is basically what you see visualized here. In this image here, where you get direct rainfall here, you get this big area just covered in moisture here, and it flows down the incline like this. Obviously, with some of the water working its way into the soil, eventually turning into groundwater. We'll talk about that later, in a process that we call infiltration. Now, as that water collects on the surface, it's going to drain the surface. What does that mean? It's going to run along the surface, it's going to pick up the sediment, it's going to erode it away, it's going to carry it away, and anything else that's there. The area which is drained by a particular river, which collects into a river or a stream, is what we call the drainage network. Okay, it's the land area that contributes water to a stream. Now, once again, this could be through runoff or this could be through meltwater. Okay, now the drainage pattern is basically all the little rivulets and channels and things like that that are going to collect into a particular river. So if you're talking about a huge river, you're going to have lots of interconnected streams and rivers. If you're talking a small little creek or brook, it might be a much smaller path. Okay, now when we talk about the drainage patterns, the drainage patterns can take lots and lots of different shapes. Okay, but they're all formed by the network of streams that are in a particular area. And so the shapes that we can have for these various drainage patterns could be things like dendritic, they could be radial, they could be rectangular, or they could be trellised. And as we see in the images below, here we have some of those particular patterns that you can see. So the dendritic pattern looks very similar to tree branches, okay? And dendritic patterns are going to tend to happen on bedrock that is relatively uniform in its resistance to weathering. So you are going to get weathering, but it's going to kind of weather relatively easily. And so you're going to get a typical tree pattern. So you can see up here, you have the smaller little streams bleeding into this one. This one are going to combine into this branch, which are eventually going to flow into this bigger branch here. And so you go from smaller body of water, or running body of water, to larger running body of water. Radial patterns are going to tend to develop on isolated volcanic cones or domes, and so they kind of flow out as if this was the center of the circle and they were the radii, ergo the term radial pattern. Rectangular patterns are going to happen on rock that is highly jointed. We talked about this earlier in the year, and so you're going to get this much more blocky, kind of looks like a cladogram that you would see in a biology class or something, but you get this much more geometric pattern that you see here. And then the last one we talked about were trellises, and trellises are going to happen in areas where you have alternating bedrock. Some of it's weak to weathering, some of it's much more resistant to weathering, and so you're going to get this pattern where you get very little going on in these areas, in the areas that are very highly resistant, and then the areas which are less resistant, you're going to get these channels forming. This is by no means an exhaustive list of drainage patterns, but this is some of the more common ones that you will see and that you may be responsible for in any classes that you are taking. Now, the drainage basin for a particular area, like we said, is the total amount of land that gets drained for a particular river. Okay, could be very different. If you're talking about the Mississippi, for example, you have this huge area right here of the United States that's swathed in green that would represent the drainage basin for the entire Mississippi. But the entire Mississippi is made up of little rivers. That's why it's a drainage basin. For example, you have like the Missouri River, or the Arkansas River, the Ohio River, and the Tennessee River, all of which drain into the larger Mississippi. Each one of those rivers is going to have its own drainage basin, categorized by obviously the different colors that you see in this image. And this particular zoomed in part right here represents one of the rivers that drains into the Missouri, called the Yellowstone River, and it has its own drainage basin that you can see all scattered all over the place right here. Now, once we've gotten a river flowing and we've gotten a stream flowing, we have to talk about the water that's in that particular stream. Particularly, we have to talk about the rate at which the water is carried by the stream. That is a term that we refer to as stream flow, the amount of water that's carried by a particular stream or river at a given time. Now, there are lots of things that can affect this stream flow value. So for example, when we're looking at a particular stream, one of the factors that affects the speed at which that water is going to flow is the gradient or the slope. So we're talking about how pitched is the river. If you have a very, very flat surface, you're not going to have a lot of velocity. Why? Because you're not going to have a lot of kinetic energy. You should have learned about kinetic energy at some point in your schooling. Okay? Whereas if you have a point where the two ends of the line are at much different heights, you're going to tend to get a lot more kinetic energy, which means it's going to tend to flow a lot faster. And so the gradient or the slope of the land beneath the river, the difference between one point in the river and the next point in the river, is going to have a dramatic effect on how fast that particular amount of water goes, so the stream flow. So if we're looking at this image here where you have a relatively flat plane here and where you have a relatively flat plane here, okay, you're going to tend to have much lower kinetic energy, and so you're not going to tend to get a heck of a lot of stream flow. Whereas along this path where you can see a much bigger incline, you're going to tend to have much more stream flow. That is going to lead to a difference in the amount of erosion versus the amount of deposition. If the water is moving quite quickly, it's going to chew away at the ground a lot more. It's going to carry away a lot more material. So that's what happens here. Once you hit the ocean here and you don't have as much difference going on, you're going to tend to get much lower stream flow, much lower kinetic energy, and you're going to have much higher deposition. So as the water slows down, more deposition. As the water speeds up, you're going to get more erosion. Now, that's not the only things that can affect stream flow. The other things that can affect the velocity or the stream flow are going to be the amount of actual water that's moving past a particular point in a particular amount of time. Large amounts of water trying to squeeze through things are going to have a different effect on how fast the river can go. You have a tiny little trickle, it's not going to be nearly as much, whereas if you have a lot of water trying to push its way through, it's going to blast its way through, it's going to eat away a lot more stuff, and you're going to tend to get a lot more erosion going on. Okay? The next thing that's going to affect it is what we call the profile. Now, profile is kind of weird. Okay, if you think of a person's profile when they're looking at the side, you can see their shape of their face and things like that. It's basically what we're doing. We're looking at a river as if it was flowing directly at us. So if we had the POV of looking at the river directly in front of us, imagine if we cut a section and we could see the actual channel that the river is flowing through. So we have what's called a cross-sectional area of the stream. Okay, we're looking at it from the head, okay, looking at the water as it's flowing. So we're looking at it from the source as it's flowing away from us. So if you look particularly at these different images, that's going to allow you to see what you're talking about when we talk about this. So for example, here you have a bunch of different cross-sectional areas. Here's a cross-sectional area where you have a relatively broad, shallow channel. Here's one where you have a narrow, deep channel. And here's one where you have a more semicircular channel. So if you were looking at these would be different examples of some versions of profiles that you might be able to see. Okay, now that is all going to affect how, how easily the water flows and things like that. So for example, if you have a relatively wide thing like this where the water can flow, the more places that the water is coming in contact with the banks of the river, the slower it's going to go. If the water is not in direct contact with any of the edges of the ground, it can flow much faster, which you can see by the arrows here. The bigger the arrow is, the faster the water is going to flow. So if you look in this particular channel, you can see on the sides here you have much smaller arrows. Why? Because that water is coming in contact with the edges of the river, the land there, whereas in the center it tends to flow much faster. And this is a general rule that we're going to have. When you're looking at a river, when you're looking at a profile, the center is, if you have a nice clean one, is going to tend to flow much faster, but you're just looking for the points that's the furthest away from the banks of the river. Okay, now sometimes rivers can bend and they can snake and they can curve like this. When they do that, we call that a meander. When you look at a river and it meanders, okay, what you're going to get is you're going to get slightly different profiles. So for example, if you look here, if we were to make a profile from A to A prime here, you have a pretty straight channel right there. As you have a pretty straight channel right there, in the center you're going to tend to have your highest velocity. As you work your way out and come in contact with more and more of the surface, the land itself, you're going to slow down. B, you see you have a curve here. When you have a curve here, what you're going to get is an uneven erosional pattern occurring on the stream bottom. And so what happens is if you look here on the outside of the curve, okay, the water is going to tend to have to go much faster, and so it's going to tend to erode a lot more material and make a much deeper channel here. On the inside where B prime is, the water is not going to travel as fast, and so what's going to tend to happen is you're going to get a lot more deposit. And then over here where it curves again, you're going to get the reverse pattern. C prime is going to where it's going to eat a lot, and C is where it's not going to eat as much. So the example I typically give my students is think of running a race. If you were going around the curve in the race, okay, if you were out here away from the main line, you have to travel a heck of a lot faster to keep track with the person or keep up with that person that has the inside track. Okay, the person on the inside track doesn't need to run as much because they don't need to turn nearly as much. Same process is going to happen here. So outside curve, run fast. Outside curve, water flow fast. Outside curve, water causes more erosion. Inside curve, water doesn't flow as fast. Inside curve, more deposition. And so once again, that's the image that we see here. So nice straight river. You have the highest velocity right there where the red bullseye is. Orange is a little bit slower. Yellow is a little bit slower. Blue would be the slowest, as long as the stream is going nice and straight. The second that we put that little curve into it, those meanders, okay, you see right here, and this image is even better, okay, On the outside part of the meander here, it's the outside, so that's going to tell us we have to travel faster, so that means we're going to get more erosion. On the inside, we don't have to travel as fast, which means the water's slower. When that happens, more material gets dropped out, and so we're going to end up with a depositional bank right here. Okay, and at B, it's relatively straightforward. There's no real curve, it's just shooting through there. And then we get to this part again right here where it does it yet again. And so you get what we call the cut banks, or where you get lots of erosion. And then the point bars are where you get a lot of the deposition going on. So, if we're talking about stream erosion, what are we talking about? We're talking about the process by which the stream is going to take those things away. Now, streams are going to lift loosely held particles, and they're going to do this a couple of different ways. Okay, they're going to take particles off the floor by abrasion. What does that mean? As the river is carrying stuff, little particles are going to get chipped and broken off. Okay, particles that are carrying, the river's already carrying, are going to hit the bottom, and they're going to slowly, change in shape and change in size as they roll and tumble along the bottom. So you're going to have that. You're also going to get material that gets dissolved out of either the soil or the rocks in themselves. As you put those rocks and materials in water, naturally things are going to leach out of them. Okay. Now, the more stuff that you have, the more stuff you carry, obviously the more erosion is going to happen, and the more easily you can lift particles and carry them away. So you're going to be lifting this stuff, bouncing this stuff, chipping away, dissolving things away, and so you get this big collection of stuff that's flowing inside that flowing or running water. So you see that in this image. So you have all these things. As the material is carried by the water, the chunks that are on the bottom are going to bounce around and chip and break, and you're going to get little particles that are just kind of easily floating around through the process that we call attrition here. Okay, and then you've got the dissolved materials that you've got going on in here. So if we're talking about the material that gets transported by a stream, we call that a load. Kind of like a truck carries a load from one point to another, a stream carries a load of sediment from one point to another. This material gets carried as either dissolved ions if it's really light, okay, and it's got, the stuff's gotten leached out of the rocks or the surrounding stream bed. It can get carried in suspension. For example, silt and clay and things like that will just get carried by the water as it continues to move. That obviously is going to depend on the speed of the water, how much it can suspend, and the particles that are too big but can still get moved around, pebbles and cobbles and things like that, are going to get bounced and rolled along the bottom. And so all that material just kind of gets pushed along as the water is flowing and going down the incline and going downhill. You have the entire combination of these things known as the stream's load. Now, what a stream can carry is known as the competence of the stream. It basically indicates the maximum particle size a stream can carry. Okay, so when we're talking about the competence of a stream, we're basically saying, okay, this is the biggest thing it can carry. It can carry anything smaller than that, but the maximum, the ceiling as to what it can carry is this particular particle size. And all of that is ultimately determined by the stream's velocity. Okay, so if we look at this lovely chart given to us by the New York State Board of Regents, okay, here we have on the x-axis we have the stream velocity in centimeters per second, okay, and on the y-axis we have the diameter of the particles with the name of that type of particle located over here. The line here represents wherever you intercept on the line determines what you can carry. So for example, if you are a stream and you travel at 1 meter per second, you would take this line until it hits the curve that's on here, and a stream can carry sand, it could carry silt, and it could carry clay. Now it could carry sand that is bigger than 0.01 of a centimeter, but it could not carry 0.1 sand, okay, or 0.09. Okay, so there are ranges. Now in this chart, you can actually see it's the same exact chart, it's just a little bit more color coded, so it's a little easier to follow. Okay, I understand the scales are a little bit different. Obviously this would be a much bigger chart, but in order to fit it into the reference table that New York State provides, they have kind of had to compress the axes a little bit. But once again, if you're looking here, anything below this dashed line would be considered clay. Anything below this dashed line in the blue space would be silt. The tan space would be sand. The yellow space would be pebbles. Then we have cobbles between these two right here. And we have boulders as anything bigger than that. Okay? And so obviously if you are asked a question in particular, you should be able to correlate either the stream velocity or the particle size to get. So for example, if I told you the stream was traveling at 0.5 centimeters per second, okay, you go to here, you go to and you'd hit right about there. So we could carry very tiny sand and all silt and all clay. Now, for example, if I told you that a particle 10 centimeters in diameter was being carried, what's the speed of the river? You go to 10, which is right here. You go across until you hit the line. And then you go straight down, and you'd be right here. Okay, so you're talking about 200 centimeters per second, give or take. Okay, so you should be able to utilize these for any particular questions you have on this particular topic. Feel free, once again, to capture this image if it is something that you feel will benefit you. Now, as a river flows, its speed is going to change. It could speed up, it could slow down. But if it slows down, then the competence of the river is going to drop. The spot on that particular chart that we were just talking about is going to drop. Particularly the y value is going to drop as the x value drops. As that changes, any particles that you are carrying that are above your competence, that are too big for you to carry, are going to get dropped off. And so we're going to lead to the deposition of sediments by a stream. Like we said, as the river slows down, it's going to drop off the material. And this is going to happen in a very organized way. And so stream sediments tend to be very well sorted in terms of size. Bigger particles get dropped first, then medium-sized particles, and then eventually the smallest particles. And so what you end up is a very neat, well-organized collection of sediments, a very neat, well-organized series of deposits placed around. So when you see this image, you can see these larger particles down towards the bottom of the image right here would have been dropped off when the river lost some speed because it could no longer carry these. But it could still carry these particles at this point. When it hit this point, the river had slowed down even more and it couldn't carry these. But it was probably still carrying the sand and the silt and the clay. Okay? And so as the river slowed down, what you basically are going to see is more and more stuff getting dropped off. Okay? And so here, when the river is moving at a particular speed, it can still travel some gravel and things like that. Once it gets to these parts, it's going to start dropping off like the sand grains, and then eventually once it gets way out into the ocean, it's going to drop off the clay and the silt and things like that, and that's going to lead to the development of obviously the different types of rocks like clay stone and siltstone and things like that that we learn, mudstone and things like that. Okay, now what streams tend to do when they erode the land away is they tend to create what we call stream valleys. Stream valleys tend to be V-shaped, and they tend to form as a river cuts through a particular landmass. So what happens is that water flows, it almost acts like a saw, and it kind of cuts away at the soil and the rock beneath it and the bedrock beneath it, right where the river is flowing. And so as it does that, it's going to carve these deep V-shaped valleys. Okay, and it's going to create steep walls if it's a relatively young river, okay, and it can create waterfalls and rapids and things like that. Now, there are different types of river valleys that you can have. If you have a relatively narrow valley, that's going to tell you that that river is relatively young and immature. Now, we don't mean it's like a child. What we mean is that it has entered that area in a relatively recent amount of time, and we're talking in a relatively recent amount of geologic time. So this could be a couple thousand years. And depending on how resistant the bedrock is, it could be even more than this. Okay, and so if we look at this image right here, okay, here you have a deep river valley. You can see the V shape right here. You could literally make a letter V right there. Very different from the U-shaped valleys that we saw with glaciers earlier. Okay, you can see it's very deep, steep walls. This is going to tell you that this river is relatively new. It's probably flowing relatively fast to have cut through this. So at one point there was rock and material all up here, and the river has just kind of sawed its way down to the level that it is now. So rivers are very much like people in that they go through stages of development and they age just like we do. Rivers are going to go through this process of development and aging, and they become what we call young rivers, mature rivers, and old rivers. So a young river, as you can see in this image, which is located up here towards the mountains, tend to exist in these kind of places. They tend to exist at higher elevations. Their valleys tend to be very steep sloped, and their channels, the path through which the river moves, also tends to be V-shaped. They're going to move very fast. They're going to have a high competency, which means they're going to be able to carry lots of things and loads. You're going to find waterfalls. You're going to find rapids. This is where you want to go if you want to go white river rafting. Okay, this is the type of river that you want to go. Now, as the river moves down in elevation and as it ages a little bit, its channel is going to get a little bit wider and a little bit rounder, almost U-shaped. Okay, and you're going to start to get most of your erosion starting to happen along the sides here. More streams are going to start to feed into it. You're going to get more things that start to work its way in. It's going to have a much more moderate gradient. The velocity is a little bit slower. It can move lots of sediment sizes, but it tends not to move things like boulders, unless obviously it's like flooding or things like that. You might get a floodplain along the outside of it when, you know, the river does occasionally flood, these areas that are going to fill with sediment. You might get those things, and you get erosion and you get deposition of both. There is a lot of water that flows in there because the river itself is a lot bigger, so you can sort of see how it's a lot bigger. Now, when you get to older rivers, right, you're going to have a much lower gradient. So you see that down here, it's not going to tend to be steep, very, very steep. And what's going to tend to happen in this case is that the channel's much, much wider. You get a lot more lateral erosion here. You're going to have huge floodplains on the side, very wide. Okay, it moves small sediments like silt and clay, and it can a lot of times have kind of almost like a muddy appearance as the river starts to flow. So if you look here, here you have your young stream, your young river cutting down into valleys, nice sharp V-shaped here. Here you have a mature stream. Okay, you can see it starts to also bend. One of the things you'll start to notice is the younger the river is, the less bends it has. The older the river is, the more bendy it starts to have. We call these bends meanders. Okay, and and much older river here, much old age right here. You see huge floodplain, and you see these gigantic meanders, some of which almost look like they're starting to pinch off. We'll get to that in a second. And so you tend to have this process happen as just a natural thing going on there. And here's some photos of actual rivers doing this sorts of thing. Okay, so when you're talking about gigantic rivers, like something like the Mississippi or things like that, those are going to be obviously much older, you know, rivers, mature to old rivers, lots of tributaries and things like that. So when we're talking about stream valleys, particularly if we're talking about mature or older river valleys and things like that, you start to get a lot of features that are critically important both to geology and in many aspects to basic human culture. One of those being the creation of what we would call floodplains. So floodplains are these large flat areas on either side of a river's banks that exist when the river crests or when the river gets too much water in it and it has to overflow its banks. And when it overflows its banks, all the material that it's carrying, all the sediment, now all of a sudden the river slows down, so it drops it. We understand that when you get these things, you're going to get huge amounts of deposition and huge amounts of material that gets laid out. And as humans, we know that this has been critically important to our development in civilizations. The Nile, the Yangtze, the Yellow, the Tigris, the Euphrates, all these rivers you learn in social studies classes, cultures developed around them, particularly with agriculture, when they could track and they could time when the rivers were going to flood and things like that in order to help them with planting and the development of agriculture and things like that. And so floodplains have been critically important. Obviously, if you live, you know, in the United States now, you've heard, or in other parts of the world, you've heard about, you know, rivers going over and flooding, and it can create all sorts of devastation nowadays. So it's kind of a problem in some ways, but it's been beneficial in other ways. Now, another thing that can happen, like we said before, was as a river starts to get older, it starts to bend and starts to twist, and you start to get the development of these curves that we call meanders. Where do they form? Well, we talked about this before. You have the cut bank and the point bar, the point where you have more erosion and the point where you have more deposition. Okay? As this starts to happen and you get this uneven erosion of the land around a river, what you start to get is this bending process. And sometimes it can get so bad that you can get the creation of parts of the river that get cut off and form what we would call an oxbow lake, like you see in the image here. This right here, this horseshoe-shaped thing, is what we call an oxbow lake that formed off of this original river as it was originally meandering out there. Now, how does that process happen? Well, what basically happens is you have the river going on like this, and the red line right here is going to be the point where you get a lot of erosion, and the yellow lines where you get lots of deposition. So as this river is flowing around this meander like this, it starts to chew away at these 2 points. As it erodes and chews away at these 2 points, the river gets closer and closer and closer and closer. You also start to get excess deposition here. Eventually what can happen is this erosion gets so much that the river just chews through here, and the river goes and follows the path of, shortest resistance, and so it just follows this straight path right here, and you're going to get deposition happening here. And so what eventually will happen is this lake, this oxbow lake, has gotten cut off from the river there, and the river's following this new straighter path. So as that river is carrying that sediment, and we said it floods over and things like that, as it, obviously it's carrying so much material and it overflows its bank, what it's going to do is right at the edges of the river, it's going to tend to form these large parallel piles or hills of material over years. So as it floods every single year at roughly the same time, it's going to drop off these piles of material. And what you're going to get is these natural little hills on either side of the river that we refer to as levees. You may have heard of these when we talk about dealing with floods or on the news or things like that. Natural levees are just these big piles of sediment that form on either side of the riverbank and can kind of protect the surrounding area from a regular low to medium flood, because the water isn't cresting over them, because those would have been deposited when you had the worst floods. Okay, and so what you'll end up getting is something that looks like this. These right here on this side, and a little bit less you can see it on this side, but this would be a natural levee formed by this particular river. As it overflowed its banks, it would have slowly over the years deposited layer upon layer upon layer upon layer of material, eventually building up these natural levees. And so you get this delta formation. So how does it happen? Well, see down here, if you look, obviously you have a big delta up here, but the process by which it's going to form, you can see it a little bit clearer down here. Here you had the river, and as that river hit the ocean, it started to drop off, or whatever body of water it hit, it started to drop off sediment along the side. Okay, eventually some of that sediment might have choked off the river, and so it took another path, or you got a difference in erosion patterns as you get this branching. And so you start to get these branching off, and you start to get the development of large amounts of material before that, and you're going to tend to get almost like a swampy regions or areas like that will occur and will form in these particular areas. So as you have that water flowing and it's carrying all that sediment and that load is being pushed along, if that river hits a large standing body of water, it could be something like a large lake, or it could eventually hit the ocean or the sea. When that happens, the speed is going to dramatically change at that point where the river encounters that standing body of water. When that happens, you're going to get a ton of deposition, and you get the formation of a delta. Now, deltas, once again, something you've learned about in history classes, are these large fan-like structures of depositional material that happen when you get that stream or that lake running into that large body of water. And so when this happens, you're going to get the massive creation of this massive area, okay? And we've seen, countless areas of our planet where these deltas have become critically important to human civilization and survival. Okay, so in this image you can see here's the river at flood stage. When the river is at flood stage, the water is obviously flowing out like this, okay? And you're going to get the material deposited. Now the bigger material is going to get deposited here. Why? Because it's in the river, it's traveling relatively fast. When it overflows, the speed drops dramatically, and so you're going to get large amounts of deposition here. As the water is flowing this way, it still can carry the finer material and deposit them out here. Now, once it's flooded, this is going to dry out, and you're going to get these natural little hills here. The process is going to happen again, and what starts to happen is eventually you get this buildup right here of these natural little levees that can kind of insulate at least the rest of the area from a normal flood. But you're going to get kind of some crazy flooding that happens, then it will breach the levees and it will just completely and totally flood the area around it, which can lead to some sort of devastation and some issues that you can run into if you live too close to a body of water. So as you get older, you think about buying a house. As nice as that river view is from your window, always remember that this is not a possibility, it is a probability. It's not a matter of if the river is going to flood, it's a matter of when is the river going to flood. And that's something we have to keep into consideration when we are building our homes. Okay, one of the greatest places of this is obviously the Mississippi River. When you have the Mississippi River and it hits the Gulf of Mexico, like you see in the image before, right here in the foreground right here, okay, originally it would have looked kind of like this when it came in, and it slowly over time, as it flowed out and created all those different branches and all that different fanning effect, it would have created this general process that you see going on right here. Okay, the city of New Orleans and large segments of this section of Louisiana and Cajun country of Louisiana, the swamps of Louisiana, are formed through this massive delta that formed as the Mississippi River entered the Gulf of Mexico, and it has become critically important, both culturally and in various other reasons, to American society. So the last type of erosion that we're going to talk about today is beach erosion. So what's beach erosion? Well, sometimes you'll hear it referred to as wave action. So it's basically the carrying away of sediments as caused by ocean waves hitting a coastline, and it could be hitting the sand, it could be hitting the rocks, it could be hitting any land that is in connection or in direct contact with the ocean and the process that happens there. So we're going to talk about how that happens and what kind of depositional features are created as this process occurs. So what we have to realize is as those waves are hitting the shoreline, they're going to erode, they're going to chew away at the surface. Okay? As those waves break, like you can see in the background that we've been looking at this entire time, they're going to chip away at the material that's there. They're going to abrade it, they're going to smooth it out, they're going to carry material away. Obviously, as the waves come in and then pull back, they're going to pull away all sorts of material. Material that's less resistant is going to get chipped away. Material that's more resistant is going to sit there. And so when we're talking about rocks along the coastline, the features that we're typically going to get with those are going to be what we call sea cliffs, sea arches, sea stacks, and sea caves. Okay, all of this is going to be formed by the same thing. As those waves come in and hit the rocky coastline, they're going to chip away and create some of the most beautiful images and some of the most Instagram worthy images that you will see. So for example, okay, here you have some sea cliffs. So as the water is come in and hit those, it's slowly chipped away at probably the limestone based on the color, or the sandstone. I can't really tell what that is. Okay, and it's created these just dramatic features. The White Cliffs of Dover, for example, in England would be examples of these. These are just the edges of continents, and as the oceans hit them, they pull away material and expose these sharp, these sharp-edged cliffs, which are just quite pretty and quite striking when you look at them. Here you have sea caves, and caves are going to form through dissolution. Okay, as that ocean water works its way into there, it's going to eat away at the material, particularly if you have materials that are easily broken down. If you have things like marble or things that are easily chewed away by the weak acids that are going to be dissolved in oceanic water, you're going to get the development of these sea caves. Once again, just breathtakingly beautiful images. Okay, arches like this famous one, which unfortunately no longer exists, but this is an arch. Right here, you would have had less resistant material, and as the water just battered it and hit it over the years, what happened? It got chewed away until all you had was this little bridge right here spanning this ocean. Unfortunately, like everything in nature, nothing is forever. This is the same image a few years later, and you can see that it just kind of got pulled off. Okay, and so then what you're left with is what we call a sea stack, which would be a freestanding piece of rock that is no longer attached to the coastline, because at some point there was an arch here, but it has been since eaten away. As you get those waves eating away at the surface, you're going to have lots of different currents that are going to carry material along different ways. If you particularly have an ocean current that moves parallel to the shore, you get the development of what we call a long-shore current. That long-shore current, since it moves parallel to the shore, what it's going to do is it's going to erode, pull sand particles here, but it's going to pull them down here. And so what ends up happening is you get the formation of what we call a long-shore drift. Okay, where you're eating away at the beach over here, but you're building the beach over here. And so basically that is a combination of the waves and the wind that are going there. And so eventually you get this downstream building of the beach here, the upstream eroding away. So you get the whole process of both erosion and deposition occurring as that longshore current moves along the land here. And finally, when we talk about the deposition that happens, well, the most common material that's going to get deposited by ocean waves is going to be sand, particularly quartz sand. Now, quartz sand is going to typically be that, powdery, yellowy, tan stuff, but you can get other forms of sand. If you're chipping away on a basalt rocks, you're going to get black sand. Black sand beaches are a thing. There are beaches that are of various colors. It's basically whatever the origin rock that was getting weathered and now is getting deposited at that particular place. But the most common depositional feature that you're going to get from waves are going to be beaches. Beaches, every beach you've ever been to is just a massive depositional feature. The ocean water carries the sand in, slows down, drops the sand, goes back, carries it in, drops it, comes back. And so you get these massive deposits of just sand. Okay, now that's also going to lead to things that we call sandbars or spits. Okay, these are just basically large amounts of sand that get deposited in particular ways. Sometimes they can get deposited way out. Maybe you have a particular part of the ocean floor where it raises a little bit, and so the water slows down there, and so it starts to drop the sand at that particular spot, and what you end up with is this massive amount of sand just deposited in the middle of the ocean. Sometimes it'll peak out and you can get these tiny little islands, or sometimes it's just underneath the water, and you can be in water that's normally 10 feet deep, but then in that one spot you have a sandbar that's 15 feet high, and so you can stand on it. So it's kind of strange. Spits are going to be sandbars that get deposited as a long train coming out into the ocean, and as the wave action kind of eats away at those, you can start to get kind of a bending and the creation of what we call a hook. And if you get a large amount of sandbars that start to hook up together and join together, you can get the creation of what we call barrier islands. Okay, so if we're looking here, there's your beautiful beach. How much would you rather be sitting on that than listening to me talk? I know. Or maybe you're listening to me talk while sitting on that. That would be awesome. Okay, and so all that you see here is just a massive deposition of sand carried by this very water as it is hitting the edge here. Okay, here you have a sandbar. So this was a just big pile of sand that was carried out. It has built up in this one particular place, and in this case you can actually see that people could stand here, but you can see how there is still sand below the water's edge here that you can't quite see poking above the surface, but if you were to stand on this, it would probably raise you to a higher level around. Okay, this would be an example of a spit. So here you have a sandbar that's reconnected to the mainland here, and so it sticks out way out there. You can see how it looks like a sandbar in the other ones, but it has since joined up with the continent. And if water was hitting that, if you had like a longshore current or something like that, what would start to happen is you get the erosion along kind of a hooked path here, and you get the development of a hook like this. So you can see this was a spit, and it has since, and you can see some sandbars in this image. You can actually see some sandbars. You can actually probably see some chunks there. You can see a spit right there. Okay, so you can see multiple ones in this one particular image. Okay, and then eventually you get the creation of a barrier island. Okay, barrier islands are basically going to be just, you have the coastline here, and you get these massive sandbars that collect here, and they form these massive islands just off the coastline. Okay, and these are, you know, very popular. Why? Because you can get beachfront property on there. So here you have a massive barrier island. If you're in the Northeast in New York like I am, something like Long Beach would be an example of a barrier island. Coney Island would be an example of a barrier island. Okay, and while they're very popular because they're beachfront and everybody wants to be on a beach, in terms of when you get a really bad storm coming in, these are going to be incredibly dangerous to live on, because if you look, you're right there at the ocean. So if you get a storm surge or you get an elevated sea level, that's going to be bad. So as we deal with things like climate change and sea level rises, barrier islands, where you have some very expensive housing in some cases, could be incredibly dangerous to live on in the future. And so that, ladies and gentlemen, is the end of our erosion and deposition PowerPoint. Once again, I hope everybody learned something from this. I hope this was useful for you. If you have any questions, any comments, if I did anything wrong, feel free to let me know down in the comments. But otherwise, ladies and gentlemen, I hope you all have a good day. Hope you have a good night, and I'll see everybody later. Next video should be coming up soon. Otherwise, everybody stay good, and talk to you later. Bye.